today we'll be quickly going through what is electromagnetic induction part, and then how we get inductance, self-inductance, mutual inductance, all those things. So this Faraday's law of electromagnetic induction, I think it is known to everyone, right? So here we can say that whenever magnetic flux linked with a circuit changes, that means whenever there is a rate of change of flux, then an EMF is always induced in it whenever a conductor cuts the magnetic flux. Okay, so it is, you can write the induced EMF like this, where E equal to N d phi dt, or you can write like here d psi dt, where psi is equal to flux linkage. Flux linkage means it is a phi linked with n number of turns of coil. Okay, so what does this negative sign signify? It indicates that it's try to neutralize its cause. Like whenever there is some current will be flowing through a coil, which will produce phi, that you have learned from the magnetic circuit. Whenever there is a current through it, then flux will be produced, and whenever this current is changing, whenever there is a di dt, then of course due to change in the current value, phi will also change. So d phi dt will also develop, and that will link with n number of conductors. So n into d phi dt will generate a EMF. So EMF will be developed in such a way that it is trying to oppose its cause, right? Like if we have a coil and we have a resistor like this, and we have a connected battery with it. So with rheostat, you are changing the current value, and that's why if there is a toroid over that, there is another coil. Okay, so flux will be linked with it. There will be d phi dt, and this d phi dt, if this is n1, this is equal to n2. So n2 into d phi dt will develop the voltage in such a way, say this is equal to E. The polarity will be in such a way that it is trying to oppose it. Like if the flux direction is like in this way, then the flux produced in this coil, N2 coil, 2 coil 2, will be in such a way that it is trying to oppose the current flow through the circuit. So this will also induce the voltage here, and that will try to nullify the current, right? So that is actually known as the Lenz law. That is also, I think, you have learned. So direction of the induced EMF is always such a way that it tends to set up a current opposing the motion or change of the flux responsible for the induction of the EMF on that coil. Okay, so that is what Lenz law, and that will give you the polarity of the voltage. But magnitude will be always same, d phi dt, and that is equal to n into d psi dt, that is equal to n into d phi dt. Okay, so we can develop, there will be the induction of the EMF either dynamically or statically. Dynamically induced EMF is what? Whenever a conductor is moving in a constant magnetic field of flux density b Weber per meter square. So here we have given an example, like this is a magnetic field, and A is the cross section of a wire or conductor lying within a uniform magnetic field of flux density b Weber per meter square. Then the arrow attached to A shows the direction of the motion, and that you will get from the uh, uh, from where you will get this expression from the framing right hand side rule, or if arrow is given, so direction is there, then this is your right hand, and
Sir,
the, sorry, continue.
sir, can you repeat that? I just came for CS class right now. I missed that first part.
Okay, huh, tell me once again. your, your voice is actually breaking. I cannot hear anything. Repeat.
अरे वॉइस चेंजर बंद करना सयन.
Okay, let me repeat once again. So I was discussing about the Faraday's law of electromagnetic induction, right? So what does electromagnetic induction tell you? Whenever there is a flux linkage with a coil in a circuit, and whenever there is a rate of change of flux, whenever there is a change of flux, variation in the flux, so that will develop that will induce an EMF in that particular coil. So that EMF can be either produced by dynamically, or it can be produced statically. So whenever there is a variation on the flux, so that we can write as disha dt, flux linkage we call. Psi is your flux linkage, and flux linkage is phi into n. So if there are n number of coil, so flux linkage psi will be known as, will be equal to n into phi, right? So n d psi dt will give you the magnitude of the induced EMF, and negative sign signifies the polarity. So the developed induced EMF in such a way that it tends to set up a current opposing to the motion, or opposing to the change of the flux produced, change of the flux which is responsible for inducing EMF in it. So here I have shown us example of statically induced EMF. So we have a battery and we have a rheostat with which we are changing the magnitude of the current. This is your coil where the flux is developed. This is a toroid, or it's a magnetic material through which this flux phi will be linked with the another coil 2, right? So this coil will, if we join it, if we have another coil and if we close it with another resistance, phi will be produced, so current will be produced through this coil, isn't it, the coil number 2? And this current or the EMF induced in this coil will be d psi dt, and that into n2 if the number of coil turn is n2. So n2 into d phi dt is the induced EMF, and its polarity will be in such a way that it is opposing this phi which is set up by the coil 1. Okay, that is what will give you the symbol E equal to minus n d phi dt. So this is due to the Lenz's law, which you have already learned. So electromagnetic induction, then Faraday's Fleming's left hand rule, right hand rule, you have learned. I hope so. So whenever we talk about the dynamically induced EMF, that we can relate with the Fleming's right hand rule, because right hand rule is your generator rule, isn't it? So what does it say? Here you see we have a uniform magnetic field of flux density B as it is shown, and it has a direction like this. And you have a coil, or you have a conductor which is having a cross section area A. It is shown here. So A is shown in cross section lying in the uniform magnetic field. The arrow attached to A shows its direction of the motion. So if it is moving, then only there will be the flux linked with the coil. There is a variation of the flux linked with the coil, isn't it? So that movement direction of the motion of conductor is shown as V here in this way, which is perpendicular to the direction of the field. Okay. Consider the condition when A cuts across the right angle to the flux, like here it is shown direction. Suppose is the length lying within the field. So if you, this is your top view, say if you want to see from the side view, this is your conductor and this is your field. So in that way, if you look at, then this is the length of the conductor L. So here this is a conductor which is of length L. Then what is your area swept by it for this V? So if in time dt, the area swept is L into dx, because we can write V as dx dt, isn't it? That is your velocity. So for time dt, there will be area swept, which is L into dx. So this is your dx. And if you want to see the side view, it is like this. If you look from here, then side view is like this. This is your L. So L into dx is your area swept for dt time. And then B into that area will give you the phi, right? So now d phi dt is equal to what? It is equal to B ddt of B into L into dx. So you can write it as BLV as I have shown here. Okay, so BLV, where V is the velocity and L is the length of the conductor, B is the flux density. Now, if the conductor moves at an angle theta like this along with the direction of the field, then this sine theta we have to take. That component you have to take. So then we can write it as BLV sine theta, magnitude wise. And if you want to express in the vector form, then you can write it as L into L is the scalar product, then V into B. So V into B is like this. So the direction will be perpendicular to this. So if you apply the rule for the cross product, this is your velocity vector, and this is your V B vector. Then V cross this is like this, and that polarity I have drawn mistakenly in that way. So you have to go downwards, right? And that you can downward to this. So you can write it like this, the direction of the current, which is a cross. So if you relate with now Fleming's right hand side rule, then that you can cross check. So middle your what is your right hand side rule? Your uh, direction of the motion is along your thumb, and your index finger will indicate your field. So if the index finger is indicating field and thumb is your direction of the motion, then your middle finger will show the direction of the current. So if you now try with the right hand side rule, then that will give you the downward direction of the currents, which you can cross check with this cross product. Okay, so this is dynamically induced EMF, and this is called also generator rule when it is induced dynamically. And next we come to statically induced EMF, which is actually developed in case of transformer. Okay, so in transformer, it is a static instrument. There is no dynamics in it. So what is happening actually? We are changing flux. We are varying flux so that we get a EMF induced in the secondary in case of transformer. So the same thing. It is actually mutually self inductance, and due to mutual inductance, it is developed in case of transformer. Suppose we have a magnetic flux through a coil of n turns to be phi in Weber in t second, uh, say relative movement of the coil and the magnet, that is equal to d phi dt, right? Since each of the lines of the magnetic flux cut the turn, one turn can be regarded as the conductor cut by phi Weber in t seconds. So average EMF is, as from the Lenz's law, it is d phi dt, and for one coil, one turn, it is this d phi dt. So if there are n number of turns, then it is n into d phi dt. Or we can write like, if the flux linkage is psi, then that is equal to E equal to minus n minus d psi dt. And from here we can write flux linkage means n into d phi dt. Okay, so this is actually statically induced EMF. So here we are doing this with the help of a permanent magnet. The same thing you can do with the help of a electromagnet or current through it. If you if it is a magnetic material, and if you pass a current through it, and if you vary the magnitude of the current, then of course your flux will be varying, keeping this thing without motion. If you keep it at static position and just vary the current through resistor, then It is a statically induced EMF. So this is the EMF induced in a coil due to change of its own flux linked with it. So there will be two things. One is due to its own flux, another is due to the flux from a separate coil. That is called mutually induced EMF. So there are two kind of EMF. One is self-induced EMF, another is mutually induced EMF. Self-induced EMF is the EMF which is developed due to the variation of its own flux. If the current through a coil is changed, then the flux linked with its own turn will also change, which will produce in it a self-induced EMF. The direction of this EMF opposes any change in the flux. In fact, the very cause of its production as per the Lenz's law. Okay. Energy required to overcome this opposition is supplied by the source of the current. Definitely, because otherwise there won't be uh, uh, any flux if it is completely opposite. So what is trying to opposes that will be overcome by taking the or drawing the energy from the source of the current. That means the battery. This property of the coil is due to which it opposes or increases or decreases the current or flux through it is known as self-inductance. So inductance will try to oppose the uh, uh, direction, the cause of it. That means the flow of current. So if it is decreasing, then inductance will try to increase this. If it is increasing, then inductance will try to decrease it. It is quantitatively measured in terms of coefficient of self-inductance L. Usually it is noted as L. Okay. So I'll come to it. And this is the property analogous to the inertia of a material body. That we'll discuss. So here we have a self and mutual inductance which we have demonstrated. So you see this is a magnetic material or core. It can be air core if it is only air, and if there is a magnetic material, then the core is a magnetic material. That's all. And you have a battery, you have a switch, and you have a resistor through which you are changing the resistance of the coil of this circuit. And this is how a d phi dt will be developed. And if the n number of turns are there in this coil, then EMF will be equal to n into d phi dt. So if there is a current I which is produced, and there is a current through it, that will develop EMF. This is polarity plus and minus, and this will be also plus and minus, which is EM rather we can write. So if the battery has a voltage E, so this will be in such a way that it is try to reduce this E minus EM. So that is the effective thing. Okay. So it will try to oppose the flow of the current. So as it is trying to resist it, so that's why it will not effectively nullify, but it will try to resist. So if we have a inductive circuit, and if there is a if we apply suddenly we make and break the switch, the current will flow like this. Like this is the variation, and accordingly you will see that EMF, induced EMF, will be developed like this. So you can see that immediately it is not responding. So if it is having a more number of coil, then say you are varying current like this, and you are getting a response like this, EMF induced like this. And if it is only having a one or two turn, then immediate action will be there. So you'll be able to see this response. So we can say that if there is a mechanical body and we are applying a force on it, then acceleration will be there immediate if the mass is less. Or if we apply a torque on a mechanical body, acceleration will be immediate if the moment of inertia is less. So that is why your inductance is related with the inertia of a body. Okay. And here this is the example of a self inductance. This is because of the phi which is mm, produced by the coil itself, and that is linked with its own flux. And if the situation is like this, we have a uh, coil, and we are passing a current through it, this I current, and that is developed a phi. So phi is having a component of phi s plus phi m. So part of it will link with only with this particular coil, and another will link with the other coil. So like this. So phi m is the mutually that phi which is shared by the other coil. So this is a mutual flux linked with the other coil, and that will develop also a EMF. And once you close this circuit, a current will be flowing through it so that it can oppose its cause, right? So this is phi m, which is actually a fraction of the phi, say a fraction of the total flux phi. Okay, so you can write this E mutual is equal to K into N2 into d phi dt. Whereas here, if the number of coil here is it is 1 for the coil 1, then this EMF is equal to N1. So EM1, this is EM2, say N1 into d phi s dt. Okay, or rather we can write as N1 into 1 minus k into d phi dt. So part of it will linked with itself, and the other part will be linked with the other coil. Okay. So what is self-inductance? It is a property of the coil that opposes any change in the amount of current flowing through it, called the self-inductance, or simply the inductance of a circuit. This is due to the self-inductance induced EMF in the coil, as I have discussed. So the self-inductance or inductance is developed due to its self-induced EMF by changing the current. It may be noted that self-inductance does not prevent the current from changing. It serves only a delay in the change. As I told, that self-inductance does not completely prevent the current to flow through it, but it will induce a delay. So if you have a circuit like this, there is a switch, there is a coil which is having an inductance, and this is your resistance. So inductance is noted by this. Now whenever you switch on a circuit, the current response will look like this. Okay, so in steady state, what you will find, it is a DC circuit. So it is a, say if it is E, then the current through it will be E by R, isn't it? Because in steady state, inductance will have no effect because there is no variation in the current, right? There is no di-dt. So it is simply E by R. So E by R is your steady state value of the current. But due to the presence of this inductance, if it is a highly inductive circuit, then that if this is your E, then E by R is that value, which is your current through it. So to reach this E by R, it will take some time. So gradually, slowly, it will go and reach E by R. Whereas if the inductance is very low, if almost negligible, you will see the immediate effect. It will go like this. It will be E by R immediately. And if it is not at all there, then we can get just like a step response. There is a immediate action in the I current. So you can see this is actually introduce a delay in the change, but it cannot completely nullify it. So your current cannot be totally zero, just it is resisting and introducing delay in the system. The inductance of a coil depends on the three factor, that is shape and the number of turn, magnetic material which you are using, so relative permeability of the material surrounding the coil, and the speed at which the magnetic field is changing. So once you close the circuit, then after the transient is over, after the switching is over, then what will happen? There is no change of current. So whenever there is no change of current means there is no inductance present. So it will have a initial action. After that, it will just vanish. So these things will be more clear when after completing this part, when from the next class onwards we'll take the transient. analysis. So in transient analysis, we'll see that after some time, after the switching part, gradually the induced EMF will be decaying and it will vanish. Okay, that's why it is not having any steady state action. It may be carefully noted that the inductance make itself felt in a circuit whenever there is a changing current. So if there is no flux variation, changing current means variation of the flux. So if there is no flux variation, then the inductance has no value. And self-inductance of a coil is called the electrical inertia of the coil. As I told that we can compare it with the mass or moment of inertia of a mechanical circuit. So it is introducing inertia. That is why it is called the electrical inertia of the coil. Now let us come to the expression. So how self-induced EMF is related with the inductance. So self-induced EMF is actually proportional to the it is trying to nullify the rate of change of current. So it should be proportional to the rate of change of current, and that proportionality constant is your inductance. So magnitude wise we can write that it is equal to E equal to magnitude of E is equal to L into di by dt, right? And this, as per the Lenz's law, we can write N into d phi by dt. So if we integrate, then we get L into I is equal to N into phi, right? So then what else we can write in the expression of your uh, inductance? Inductance can be written L as N phi by I, isn't it? This is the expression of the inductance. Now what is our phi? If I current is flowing through it, if it is a magnetic circuit, we know that in case of magnetic circuit, phi is equal to B into A. Agree? Already we have learned this magnetic circuit. Now what is B? B is equal to mu 0 mu R into H into A, right? Then what is our H? As per the Ampere circuital law, H is the magnetic field intensity or strength, which is equal to Ni by L, where L is the length of the magnetic circuit. So we can write it like Ni by L, which is the length of the magnetic circuit, into A is the cross section area of the circuit. So this phi whole thing, if you now substitute here, then you can get L is equal to N into mu 0 mu R N I by L into A into 1 by I. So this I will cancelled out and you are left with mu 0 mu R A N square divided by L, where L is the length of the magnetic circuit and A is the cross section area of the magnetic circuit. N is the number of turn, mu 0 is absolute permeability, and mu R is the relative permeability of the magnetic material which you have used. Okay. So this is the expression of L, and its SI unit is Henry.
Sir, sir,
Yes.
mu is the relative permeability of the core of the coil.
Hmm, hmm, hmm.
Okay, sir. Thank you, sir.
So when in case of mutual inductance, what happens? In case of mutual
So my
inductance,
can you show previous page once?
yes.
Thank you, sir.
Okay. So in case of mutual inductance, same thing, only we'll just write in case of phi, we'll just write it is phi 1 2, which is linked with your coil N2. So this is the phi 12 which is linked with the coil N2, and that is multiplied with N2 because it is induced here in coil 2, right? So M is the mutual inductance due to this current I1. So M into I1 is equal to N2 into phi 12. So phi 12 is also due to your what? Due to your current I. So this phi 12 again you can write like this. Phi 12 is equal to B into A, where A is the cross section area. So if you, it is a air gap, there is a it is a air core circuit. That means there is no magnetic material shown. So that cross section area is the cross section area of this coil. So B into A. So B12 rather we write into A. And what is your B12? B12 is equal to mu 0 into mu R. Here it is a air core. So mu R is equal to 1. Simply we can write as mu 0. And then what else? Into H12. So what is your what is your H here? It is MMF equal to Ni by I1 divided by this length. So now you have to consider this magnetic circuit, and if the length, if it is, we take it as circular form, then if this is your radius R, then we can write as 2 pi R. So that is your L, and that you can put here, and then in the same way you can find out the value of mutual inductance. So this is already shown here, just go through it. So this is the expression of your self inductance, and this is the expression of your mutual inductance. So only thing is here it is n square if it is a n coil, and here it is n1 n2. Why? Because here this is in case of this is n2, so this term will come as n2, and for 1 to n1 will come. So n1 n2 term we will get in the expression of the mutual inductance. So this is mutual inductance. Okay. So now what is the coefficient of the coupling? So coefficient of the coupling between two coil is defined as the fraction of the magnetic flux produced in it. Coefficient of coupling between two coil is defined as the fraction of a magnetic flux produced by the current in one coil that links the other. So if we just go back to the same expression here, what is your can write like this: your M into I1 is equal to N1 N2 into psi 12, isn't it? And in the same way, if we have a coil like this, this is your I1 current. It is a air core circuit, let us assume for the simplicity. And if this is your I2, so what is your, if this is phi 12 for both the coil, if we can write again mutual inductance for I2 is equal to N1 into phi 12. So what you can write that in both side if we can write this is M12 and M21. So these are same actually, M12 equal to M21 for this particular circuit. For us in any circuit which is mutually coupled, this mutually coupled phi cannot change. So that is why mutual inductance also cannot be different. That is why if we put the expression of this, so your M square will be equal to N1 phi12 by I2 into phi12 into I1. So if you just change their position, like if you bring I1 here and if you bring I2 here, this side, you can write like this. Now, as I told that phi12 is a fraction of total phi. So it is this. So that if we substitute, it will become K1, K2 into N1 phi1 by I1 into phi2 by I2. So we can write like M equal to K1, K2. Here we can write L1 Hello, am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
So here we can show that if you take now square root, your aim will be equal to uh, root over K1, K2 into L1, L2. So mutually inductance is proportional to L1, L2. Now when we take this K1 is the fully coupled, so there is nothing left with the self inductance. This is the ideal if that is the ideal situation, then we can put K1 equal to 1 and K2 equal to 1, so we get M is equal to L1, L2. Okay. So now if we have the series inductors in series, then there'll be mutual inductance between these two coil, as we can see here. So it is aiding and it is resisting or opposing. How come we write like this? It is aiding and opposing. We can write because by the change of the flux, so direction of the current. If current is flowing through this their south pole will be produced, north pole will be produced, and the flux direction will be like this. And in the same way, if it is current is going in the same way, and if it is wound in the same manner, then here also south pole and north pole, it will go like this. So these two are additive, and whenever it is additive, then the mutual inductance can be written as L1 plus L2 plus 2M. So how can you write like this? This is your L1. So for the first one, same current I1 is flowing through it, so in the EM is equal to L1 di1 dt, magnitude wise I'm writing, plus M into di1 di by dt, because it is aiding. And the same way for the second coil, L2 into di dt plus M into di dt, because it is aiding. So we can write it as L1 L2 plus 2M di dt, which is your L equivalent di dt. So it is the equivalent inductance. Just like the series resistance, we can find when the inductors in series and when we have this dot convention. So whenever they are adding, just note the dot convention. So current is entering like this. Here also current is entering like this. So the same direction, clockwise. So we put two dots here. So this two dot in the beginning only, if we put these two dot, that indicates it is aiding. And if we draw the circuit in the other way, so it is in the other way round. So it is n pole here, it is counterclockwise. So here Sn, the field line will produce like this. Polarity is this. Here n means they'll generate and they're opposing. So in that case, we'll put the dot like this, like the way it is shown. So they have not shown exactly the direction of the winding, like the nature of the winding, just by presenting these two dot in the two different location. So the first one it is entering, and for second one it is outgoing, means the mutual inductance is opposing. So it is minus, and here it is plus. So what we'll do, in place of plus, we'll just put L1 minus M di dt plus L2 minus M di dt. That's all. And then if we add them up, we'll get L equivalent is equal to L1 L2 minus 2M. Okay, so your effective thing is we can write plus minus as per the dot convention, the equivalent inductance. So if we have a complicated circuit and we have a two depending on the dot convention, we can write plus or minus for the mutual one. So whenever your M is equal to 0, then it is simply L1 plus L2, just like your resistance, which is R1 and R2. So now let us come to the inductor which are in parallel, and we'll take up the direction of the current. Here we can see this is clockwise, here also it is clockwise. So here it is north pole and south pole, north pole and south pole kind of thing. So flux line is producing here, and here also flux line will be produced like this. So they are opposing one another, so we'll take M, which is minus. So in that case, what we'll write in for this particular thing, for this particular diagram, we can first write I is equal to I1 plus I2. So di dt is equal to di1 dt plus di2 dt, right? This is equation 1. Then we can find out the drop across it. Drop is equal to L1 into di1 dt minus M into di2 dt. Similarly, L2 into di2 dt, sorry, it should be uh, the other way around. It should be uh, opposing. Now we'll write it like this, di1 dt here. So now we can write L1 minus M into di1 dt is equal to L2 minus M into di2 dt. So we can write di1 dt is equal to L2 minus M by L1 minus M uh, di2 dt, isn't it? So if you substitute the whole thing in equation 1, then you can write di dt is equal to L2 minus M by L1 minus M plus 1 into di2 dt. So L1 L2 minus 2M by L1 minus M. So this you can write. So your di2 dt you can write in terms of di dt as L1 minus m divided by L1 L2 minus 2m into di dt. Now what is this expression? What is the expression, voltage expression? It is L2 di dt2, we can write voltage is equal to, we can write L2 into di2 dt. So you simply put their value here. V is equal to L2 into di2 dt. So if you substitute here, you can get the value in terms of V is equal to some L equivalent to di dt, and then just write it there and you will get the overall expression. Okay, for the inductors. And whenever you have, it is actually L2 into L1 minus m by L1 plus L2 minus 2m. So this is your overall expression. So whenever your M becomes 0, whenever there is no mutual inductance present, it is simply L1 L2 divided by L1 plus L2. So just like the parallel combination of two resistors. Okay. So with this, I'll just close today's class, and from the next class onwards, we'll try to find out the uh, mm, uh, transient whenever we have a inductance, and what happens whenever we have capacitance and resistance together. For the switching, what kind of transient we'll expect. And here is the expression of the energy stored in the magnetic circuit, that it is very simple. Energy is equal to voltage into current, power equal to voltage into current, and if you integrate it, it will become half Li square. And now when you put the value of inductance, self inductance, you will get this. This L won't be actually present, this I should remove. So this is the expression. So magnetic energy per volume, A into L is the volume of the magnetic material. So that is equal to half into BH. So it is the expression of the of your. So we can also show that the area under BH curve is equal to your magnetic energy. So this is all about your magnetic circuit, which is there in this particular course, and everything which you have learned, that magnetically dynamically induced EMF for the generators, all those things are also applicable. I'll ask you to go through your 10 plus 2 level, that part of your 10 plus 2 level course. So with this, our magnetic circuit is complete. From the next class onwards, we'll start the transient analysis. Okay.
Sir, one doubt is there.
Okay, tell.
Sir, while estimating the direction of fluxes for the self-inductance and the mutual inductance, so mutual
Hmm.
inductance you are giving the value that these are opposing, so it will be minus, and
Hmm.
if it is aiding, then it will be plus. So, sir,
Hmm.
for self-inductance will not do anything like that, because that also depends on direction of current, or it will not depend self-inductance, the plus
Now, in
minus.
case of self inductance, we have, well, let us come back here. This is the thing, na? Self inductance, there will be, if we just note it down, there is no opposing thing, na? Here, whenever you have a flux line, sorry, I'll just put it in the. So you have a current through it, and this we can see again, it is a south pole, north pole. So flux line will be produced like this, and this flux will produced in such a way that a EMF is induced in the circuit, and this EMF should have a polarity which will oppose your flow of current. So it will be automatically developed in that a way, in such a way that it is opposing its flow of this current, right? Try to oppose its cause. But whenever you have another one like here, so here we have a chance, like the way we are, this flux is produced whenever we energize this circuit as well. So this will have a flux which will aid this flux, Anyway, this is hold, like here this flux which is produced for the self inductance of this particular coil will try to oppose the polarity. So if it is the polarity here, that polarity will be this only. But for the mutual inductance part, what happened? Other coil may be adding this flux. So whenever it is adding, then that will be added up. So then the self inductance L1 plus M1 will come up. But whenever it is opposing, then this inductance property, that means its electrical inertia will try to reduce if the flux is less. So in that case, we'll write L1 minus M1. But that calculation we cannot do here because there is no such another circuit which is aiding or opposing these flux lines. Whatever flux lines is developed, that is due to the coil only which is present here. There is no other coil or no other flux or no other magnet around or magnetic field around which is aiding or opposing this flux. So whatever L is there, it will be L only, and that L will try to develop a EM which is resisting the polarity, right? Am I clear now?
Yes, sir. Yes, sir. So, sir, basically the series, sir, actually I had a doubt in that series circuit why the sign of L is not been taken care of. So, sir,
So
basically because both the coils will oppose the current in the principal circuit, but the mutual inductance will depend on the directions which in the of the
like the
flux
flux direction here,
of the other side.
if there is no mutual inductance, then m is 0 means it is mutually exclusive. There is no sharing between these two coil. If we take that ideal condition, if it is done in such a way, then this em1 will be, if this is your total e, this e will be such that it is em1 plus em2. So polarity will be what? Plus minus. In that way, this is EM2. So EM1 is nothing but it is L1 into di dt. And this is equal to L2 into di dt. That's all. There is no interconnection between this L1 and L2. So it cannot increase L2 or cannot even decrease L2. Right? Or whenever it is adding, we write the same thing as L1 plus M here and L2 plus M here, in that way. Okay, so that is not actually, or we can write as minus also. So whenever there is no sharing between these two, whatever EM is produced, that is exclusively for this particular coil L1. Right, so there is no flux which is aiding or opposing this flux produced by the current through it for this particular coil. So whatever flux is produced, it is produced in such a way that we are developing or inducing an EMF which is having a opposite polarity of the of this E. Okay.
Okay, sir. Thank you, sir.
Sir,
Yes.
sir, the mutual inductance value AM is same for series and parallel circuit both. Means
Mhm. For
K factor.
series, for this one is same.
Okay, sir.
This
Thank you, sir.
K, this one. Okay, there are many problem. I don't know whether I'll get time or not. So interesting problem, which are interesting, that is already solved in the book by Mehta. And whatever I taught today, it is also everything you will get it in the book by Mehta. So I will request you to go through this path and solve the problem which are specifically solved in the example. And then you try exercise, because example you will find many interesting problems are given. Okay, so so I am not just simply copying from there and solving. So I'll ask you to refer that and then try to go through the exercise and the example. Okay.
Okay, sir.
Okay.
Thank you, sir.
Okay, that is for all for today. From the next class we'll start the your transient analysis for the RL and RC circuit. Okay, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.